Hey guys, I decided to try to be on time today. Okay, well, let's continue doing what we're doing. I want to go and finish up this interesting result on recurrences where we're going to use the matrices and the linear algebra to go and finish this up. Okay, so let me switch to the blackboard 1 second. Here we go. Okay, so just a quick review of where we were from last time. What we had found out is we said, look, let's think about, this is just going to be a very quick from the top. I'm doing it so that we get very comfortable with the methods. But suppose I have a recursion, and the recursion is something like an is equal to an minus 1, that was capital an minus 1, plus capital B, an minus 2, plus capital C, an minus 3. The big idea was just to go and multiply matrices again. And with this thing, we could say that if I took, this time I'm going to run it as an plus 2, an plus 1, an. Last time we did it with an plus 1, an minus 1. The result would have been the same. But I've gotten this guy, and I can rewrite this guy as, we did a matrix product, and the matrix that we had was the ABC, 1, 0, 0, 0, 1, 0 matrix raised to the power n times, this would be A2, A1, A0. And then the big game became, let's go and figure out how to take the power of this matrix. And to take the power of this matrix, we wanted to turn it diagonal again. And the way that we tried to turn it diagonal is we said, let's look for some lambdas and some v's. It's like lambda 1 and a vector v1, all the way to a lambda 3 and a vector v3. And we wanted to find these lambdas and these vectors for which we had the following situation. We wanted to have that if I took a, b, c, 1, 0, 0, 0, 1, 0, if I took that and I multiplied it by the vector, like say v1 for example, but this would be true for all values of 1, so v1, v2, and v3. And this is supposed to be equal to lambda 1 times, v1, and so on. And the reason that this was important is because then we could write some interesting matrix product. Then we could find, so it would turn out that if I took the ABC, and this I'm just reviewing, we've done this a bunch of times before, but because I know that a lot of people only either recently learned this matrix stuff or it's fresh, I just want to keep doing it because it's neat. And after you see it this many times, you won't ever forget. Like, this is why you care about finding vectors for which matrix times vector is a multiple of the vector. I'm going to draw this as v1, v2, v3 as columns. Annotated like this. Okay, this thing is equal to the same v1, v2, v3 as columns. But now multiplied by your diagonal matrix, which is the c's. Sorry, the lambdas. Lambda 1, lambda 2, and lambda 3. And the rest of the stuff is 0. Okay, and where we got to last time was, how do we know we can multiply by the inverse of this matrix? It would be great to multiply by the inverse of the matrix. And the fun fact is that if the lambdas are all distinct, you can always multiply by the inverse of the matrix. So here's a neat fact. We won't completely prove the neat fact, but I'll relate it to something else that's also a neat fact that we could actually go and show if we had more time. The neat fact is, if the lambda 1, lambda 2, and lambda 3 are distinct, then this star matrix is invertible. Okay? And finding out that the star matrix is invertible is actually related to showing that there's no way to make a linear combination of the v1, v2, v3 that happens to give you a zero vector. Okay? And so why was this true? We had actually Subhashis showed us last time some way that you could do this for 3. I'll show you a way that's related to how you do it in general. The way this is because, what would that mean? Well, proof of I'll write proof in quotes because we're going to rely on something else, but we'll rely on something else that's also well known. The proof in quotes of this neat fact. What we do is we say, well, assume for sake of contradiction that it's not invertible. So assume that not invertible actually, then there's some stuff from matrices that tells you that if a matrix is not invertible, then there's a way actually to write a linear combination of the columns, meaning like a C1 times the V1, a C2 times the V2 plus a C3 times the V3, so that that linear combination of the columns adds up to 0. And not only are there some C1, C2, C3, but actually these C1, C2, C3 are not all 0. There are some constants C1, C2, C3, not all 0, so that if I wrote C1 times this V1 plus C2 times the V2 plus the C3 times the V3, this is the 0, 0, 0. And here's where we sort of got to last time, and we had an interesting proof of what to do next. But here I want to do it with actually more matrices. So one way I can think of this is I actually first want to think about what happens if I take this guy and I multiply it on the left by this matrix, this ABC matrix, which we called M. This ABC matrix here is what we called, oh, I don't want to use another pink. Let's use this white one. This matrix was M. If I multiply on the left by M for this, actually it's really nice because when you multiply M against V1, you just get lambda 1 times V1. Okay? So what I'm going to do is I'm going to multiply on the left by M, and I'll just get like C1 times lambda 1 times this V thing, plus C2 times lambda 2 times this V2 thing, plus C3 times lambda 3 times the V3 thing. The important thing is if I multiply in a lambda from the left, then multiply in M from the left, the M hitting a V something gives me the lambda something times the V something. It just rescales it. It's really nice. So let's do that a couple of times. I'm first going to rewrite this piece up onto the next screen, the C1 V1 thing. Okay? So I know that the C1 times V1 plus a C2 times a V2 plus a C3 times a V3, that's equal to 0, 0, 0. But what else I also know is I know that if I took an M multiplied by a V anything, let's just write V2, that's just going to give you a lambda 2 times your V2. That's really nice. So whack it by the M on the left. So what happened here is you just left multiply by the M. Okay, if I do that, I'm going to get the C1 is just a number. So it's just like if C1 was like 50, it's just like 50 times whatever happens when I take the M times the V1, which is lambda 1 times the V1. So that means that I'll just get the C1 and a lambda 1. Actually, I'm going to put them in the, well, I'll leave them this way. C1 lambda 1 times this V1 plus C2 lambda 2 times this V2 plus C3 lambda 3 times this V3, and that's equal to 0, 0, 0. I want something that's going to look sort of like a pattern. So I'm actually going to do it again. I'm going to left multiply one more time by this M. So I'll do it again. And I'll get, actually, if you think about what happens, I have like a C1 and a lambda 1. These are just some numbers that are just multiplying my vector by some length. The real interesting thing happens when the M hits the vector. And when the M hits the vector, oh, it's still V1. So M times V1 is giving me a lambda 1. Can anyone tell me what would be in front on here, just to make sure people are following? If I do it again, what kind of an equation am I getting? Thomas.
You just get all the lambdas are squared.
Yeah. is lambda 1 squared times v1. Because what just happened is that, the c1 and v1, they were just like some numbers like 3 and 17 or something. 3 times 17 times a vector. That's like how much you're scaling it. Oh, I want to have m times that. So that means that I'm just going to also scale that vector by another lambda 1 as well. And there's a c2 lambda 2 squared v2 plus c3 lambda 3 squared v3 equals 0, 0, 0. Now, there's a reason I did all of this. It's because actually all of this can be written as some kind of a 3 by 3 matrix product. And what do I mean? Well, let's look at this first thing, okay? Or actually, the first thing is hard to guess what the matrix product would be. Let me look at the third one. The third one I can get something interesting out of. This third one, I can rewrite as a product of a matrix and a vector. And the matrix I want, let's get started with this. I want someone else to help me finish it. But the matrix is going to have its columns. I wrote this a little bit wider because I need some more space. In fact, the columns I want are C1 as a number, scaling the first vector v1. And then I want C2 as a number, scaling the second vector v2, which is a vertical column. And then I want C3, which is a number, scaling the third vector, which is a column. Okay, so I wrote this as a square because it is a legitimate square. What just happened here is I said the v1 is a vector, it's 3 tall, and the c1 is a number, maybe it's 5. And that just means I take that vector and I just scale everything by 5. I claim that if I took this thing and multiplied it by a certain column, that's equal to 0, 0, 0. Can anyone help me fill in what that column would be? This is about matrix multiplication. How does this work? We have a bunch of people. Jack.
I believe it's lambda 1 squared at the top.
Lambda 1 squared at the top, then lambda 2 squared next, and then going down to lambda 3.
Yeah, so this is all the squares. Lambda 2 squared and lambda 3 squared. I want to pause for a second and like digest what just happened here. See, the reason why this works is because if you look at what this this left-hand side is, I just have like some numbers, c1 lambda 1 squared, okay? But what would like the top element of this first thing be? Because this left side is like something plus something plus something. And let's look at the top element of the left side. The top element of the left side is just going to be c1 lambda 1 squared times the top thing in the v1, plus c2 lambda 2 squared times the top thing in the v2, plus c3 lambda 3 squared times the top thing in the v3. Oh, that's actually exactly what this is doing. Because if you do the matrix product, you grab this guy and you put it across the top. And what you get is you get the lambda 1 squared times the c1 times the top thing in the v1. Did that sort of make sense? It's actually really neat what matrices let you do. Matrices are just ways that let you organize if you have repeated stuff happening. It organizes it all in a way where you can say, yeah, all this complicated stuff, all I'm doing is I'm just saying, I want to have this lambda 2 squared, all these squareds, lambda squareds, to line up against all of these pieces of the vector, v. Now, why did I do that? I did that because this is the easiest one to see what comes from here. I want to do that for the second one too. Now I'm going to clear out some space. Well, the second one, I can also write something. Can someone help me out? What would the second one give me if I wanted to write it as a big square thing times a column thing equals another column thing? I want to see if people are following. What can I do here? Isain?
Would that be again C1, V1, C2, V2, and C3, V3? And on the 3 by 1 matrix, it will be lambda 1, lambda 2, and lambda 3.
Yeah. And then this is just going to be lambda 1, lambda 2, and lambda 3. Okay, and 0, 0, 0. Huh. So I just did that for here. For completeness, I think I would like to do something up there too. Any ideas? What would be a reasonable thing to do for this first thing? Braden.
We could write that as the C1v1, C2v2, and C3v3 matrix times the vector 1, 1, 1 is equal to 0, 0, 0.
Yeah, let's hit it with 1, 1, 1. That one works. That's 0, 0, 0. Okay. Now, why did I go through all that effort? Advait.
So you just found, so since all the lambdas are distinct, right?
Ah, all the lambdas are distinct. Yes, they are.
Now you've found three completely different independent vectors that get mapped to 0 when you hit it with that C1v1, C2v2, C3v3 matrix. And that means it has to be the 0 matrix.
Yes, thank you for the drama. So basically what's going on is that these three are like very different vectors. So there's something about like if I have a 3 by 3 matrix and I take like three what are called linearly independent vectors and you multiply them in and you're all getting 0, that actually tells you that the solution space of that matrix times vector equals 0 has all three dimensions. Actually, that means that that matrix is invertible. There's another way to see this. I wrote this in a way because I want to tell you another interesting fact. This is the fun fact. So if I went and, like, let's put that one matrix, I can write the whole thing as a ginormous matrix product. This times this is equal to this. So I have a lot of space. Can anyone help me fill this space in? There's a reason I'm doing this, actually. It's because I want to relate different areas of math together. What Advait said, by the way, is true. The fact that somehow this 1, 1, 1, lambda 1, lambda 2, lambda 3, and then the squares, they're all like independent, then that means that the matrix in front is actually the 0 matrix, which is awesome. Chris?
So do C1, V1, C2, V2, C3, V3, and then stack 1, 1, 1, lambdas,
Stack
and then
time.
lambdas squared.
Yes, let's stack. Lambda 1, lambda 2, lambda 3. Lambda 1 squared, lambda 2 squared, lambda 3 squared. Okay. And what's that equal to if I multiply? Well, 0. All zeros, all zeros. Because remember, the matrix multiplication is if I have the same matrix multiplied by different columns, and I slap all the columns together, which is what we just did here. If you slap all the columns together, the output will be the three outputs slapped together. Oh, but all the outputs were 0. Now, the reason this is nice is because, you see, what Advait said about how these are three independent vectors, there's actually, that's one of the facts. That's the fact I wanted to use. I wanted to just draw attention to the fact that this particular matrix is famous. And it should be. It looks nice. 1, 1, 1, lambda 1, lambda 1, lambda 1, lambda 2, lambda 3, and then the squares. It looks so nice. Surely somebody has studied this before. And there is somebody who studied it before. It's called the van der Monde matrix. We've seen that name before, by the way. Van der Monde, there was also this van der Monde's convolution, which was some interesting way of like multiplying things, binomial coefficients together. At this point, you're probably like, van der Monde's a genius. He must be some great mathematician. It's actually quite interesting. If you look up his Wikipedia page, obviously that must be true, right? It says that he was a violinist, and apparently he got into math later in life. But he did, he has done two very well-known things. One about like binomial choices, and one about these matrices. And in particular, this particular matrix is invertible. In fact, actually, real fun fact, not used, I mean, we won't need it for this class, but it's just like nice for you to know. The determinant of this matrix is incredibly nice. That's called the van der Monde determinant. And if you have a matrix which just like ones, lambdas, lambda to the next powers, and you can have like n by n of this form, actually, the determinant, I'll write the determinant of this particular one, it's just lambda 2 minus lambda 1, lambda 3 minus lambda 1, lambda 3 minus lambda 2. It factors. It factors into all these differences between lambdas. And that's extremely satisfying, by the way, because when's the determinant 0? for this thing with like this particular matrix with a bunch of lambdas, when is that determinant 0? Advait.
When the lambdas are the same, or like two
Yeah.
of them.
Whenever you have two equal lambdas, then if you look at that matrix, you're like, well, yeah, I got then, two equal rows, so the determinant is 0. Bam. But if you look at this factorization, if you've got two equal lambdas, this is finding all the ways to find two different lambdas and subtract them. So this is a very beautiful fact, this Vandermonde determinant. However, the punchline is that darn thing is invertible, because the lambdas are distinct. So this is invertible, so you could just multiply by its inverse and conclude that the C1v1, C2v2, C3v3 is the 0 matrix. Okay, so that's like, this is the fact that we use, the Vandermonde determinant. But that's like a computational fact that's just true of any time you write a matrix of this form. So that implies multiply, like so, multiply by its inverse. Boom. Once you do that, multiply by its inverse, the whole thing is gone. And I now get that this C thing is all 0. How does that finish our proof? Remember what we were trying to do? Oh, Isain, did you want to add something or say something or finish it?
Oh, that was from before, but if we say that means like C1 and C2 and C3 are 0, which contradicts like that they're not all zeros.
Yeah, that's it. Remember, we started off by saying, assume that the C1, C2, C3 not all 0. Look, how in the world can you make this thing equal to the 0? Well, there was one thing we assumed, which was that the V's are not like all 0, right? So the V, we assumed the V1 is not all 0. If the V1 is not all 0, the only way you can get C1, V1 to give you zeros is for C1 to be 0. So actually with this one, with one flash, you get that the C1, C2, C3, they're all 0. And that finishes this. And I'll write, since we assumed that the V's, let's call it Vi, are not 0, 0, 0, thus all of the C1, I'll call it all of the Ci's, are equal to 0. Boom. Okay. So that's actually the theory behind, like, if I happen to have distinct lambdas, like, I will get to invert the matrix. And the one piece that we use is this, like, magic Vandermonde determinant, which, that's actually, like, just some numbers that you could play with if you wanted to. Okay, so now we're ready to go and get the magic formula for what happens with these three-term linear recurrences. Three-term linear recurrence, we now know we can go ahead and invert as long as the lambdas are distinct. And that's what we'll be doing. We'll be finding results for if they're distinct in this section, and in the next section we're going to deal with the case when you have repeated. Okay, so now the only game in town becomes, what lambdas can I use? So that's where we want to know now, how do you get this lambda equation to work? How can you find lambdas so that you have not all 0 V's that make this work? Well, we saw that last time. That was where you said that's the same as this matrix equals, this matrix times the V equals like lambdas on the diagonal times the same V. Are people with me on that? Because now we're just going to subtract that off. And we're going to get a determinant equation. Okay, now it boils down to when if I took this ABC 1 0 0 0 1 0, when if I take this thing times a V, it's equal to lambda times B. And again, I'm going to write the lambda as the lambdas on the diagonal. Now they're all the same lambda because I just want to know which lambdas make it possible for this to have not all 0 solution for V. When this has solution with the V not equal to 0, 0, 0. And I hope this also gave some color then for why I care about the V not being the 0, 0, 0. It was extraordinarily powerful in that last bit of the last proof where we just used, bam, the V's are not all 0, that's why the C's are all 0. Well, for this, we did this before. Oh, I have a bad habit of when things are 0, I just don't write them in the matrix, but I'll put back the zeros. Okay, so that's there. And now let's just do what we did before. You subtract off, right? The answer is exactly when you take the determinant of, you now subtract the matrix on the right from the matrix on the left, and you get A minus lambda, B, C, 1, negative lambda, 0, 0, 1, negative lambda. Exactly when that's equal to 0. Okay, now how do you take the determinant of a 3 by 3 matrix? There is this like funky trick you can use that some people learn in school, which works for 3 by 3 matrices, and I think it's not a reasonable tool. I don't know if anyone's seen this before. You like write 2 more copies of the columns over there, and you just kind of like draw these things across and those things across and multiply. That's actually a very bad formula to use because it absolutely does not generalize. Or that symmetric Gauss elimination thing. Yeah. We can do cofactors, we can do Gauss elimination. Let's do cofactors, okay? Cofactors means we kind of go across a row or a column. Any preference of where you want to cofactor this thing? Cofactor, the easiest way to think of it is like, I'll just go across the top. I'll take that thing multiplied by what happens if I block off those 2 pieces and determinate the rest, right? That's what you always do. Third column. Let's go on a third column. So we will take the determinant where we go along the third column. Now, whenever you do this cofactor expansion, what happens is you will go through the column and you'll say, let's take this first guy and multiply by what I get of the determinant when I block off the row it's on and the column it's on, and there's a plus or a minus that I use. And in fact, if I use the third column, this is going to be with a plus up there. Like the pattern for the determinanting of the thing that we do, the determinant, let's call it the sign pattern. It's just a chessboard. It's like plus on the top left, minus plus, minus plus minus, plus minus plus. Are people familiar with this kind of an idea? It's like when you're doing the cofactor expansion, you decide on one row or one column to go on, and then as you go along it, you go and use the sign times that particular number, multiplied by the determinant of after you block off that piece. Determinanting. Yeah, I'm trying to figure out what is the right verb for this. I said it in my Putnam class. I couldn't find a good verb for determinating something or whatever. But let's keep going. So what do we do here? Determination. Actually, I think that's right. You guys did come up with that in my class. There were some people who came up with the idea to call it, we are determined to determine, forget it. Okay, so let's keep going. So this is going to be C times the determinant of the inside, okay? So this is going to be C times the determinant of 1, negative lambda, 0, 1. And then it's going to be, the 0, I love 0. Forget the 0, it's gone. No more 0. So then we don't worry about that term. And then the last thing is just going to be a plus, a negative lambda, times the determinant of, you block off that, you block off the bottom row, block off the right column, and you get A minus lambda, B, 1, and negative lambda. Whew, what's this? Well, it's supposed to be 0. Okay, so now let's determine the 2 by 2s. I'll do the first one, that's easy. That's C times 1, okay? This is just C. Plus negative lambda times, can someone tell me what to put there? What's the next one? You guys are great. What do I put on the second one? Minus lambda times something. Raise hand, it's in.
Minus lambda times A minus lambda minus B.
Okay, and then minus B. Now I have to do some expanding. Okay, so this is C plus negative lambda times, negative lambda A plus lambda squared minus B. Okay. And now let's continue cleaning this up. So I get C plus, what is this? So I get a lambda squared A, I get a minus lambda cubed, and I get a plus lambda B. Well, let's tidy this up. Let's just take this thing and like rearrange it as a normal polynomial where you might have a lambda cubed. Okay? And actually, I like to have my polynomials where the sign on the lambda cubed on the biggest term is positive. What is this? Can someone tell me what I'd get if I rewrote this thing as lambda cubed, blah, 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 equals 0. I'm going to multiply left and right by -1 and do some rearranging. I'm supposed to get a polynomial in lambda. I want to know, like, which lambdas will work. I hope I can find 3 different ones. And I need to say that I got a polynomial just to solve for lambda. What is that polynomial? Braden.
It comes out to being lambda cubed minus lambda squared a.
Okay,
Plus,
I'm going to rewrite it as a lambda squared. All right, because that, yeah,
minus lambda b.
Yep, I'm going to flip that around.
Minus c.
Bam! That's cool. Wait a second. This is just like too nice. So when you get to here, you're like, what? So we did all this crazy work, and it turns out that is this nice? That's why people teach these like linear recursions. Because remember, when we did it for the 2-term one, what was the 2-term one? It was just lambda squared minus a lambda minus b. Oh, the 3-term one is lambda cubed minus a lambda squared minus b lambda minus c. Actually, by engineer's induction, we now know what it is for all of them. If we had done this for 7, we'd know for sure. But 3 is good enough. So actually, this is neat. This is actually the fundamental theorem of like these linear recurrences. Now all the stuff that we have done, that's just the theory that justifies this fact. I will not actually be putting on the exam that you have to know all of the linear algebra stuff, but I just can't possibly teach this class where I just say, hey everyone, magic formula, that's how it works. No. Hopefully you at least saw some other stuff and saw that Vandermonde was cool and he plays the violin. But let's keep going. So we got this thing and we just need to know the roots, right? So if you found this guy, like here's how you solve it. 3-term linear recurrence. Get this thing and suppose it has 3 distinct roots. Oh, then you get to invert the matrix. Then what? Now we got to do the blob math. Okay? So far, what have we found? What have we found is that for the an equals capital A, an minus 1, plus capital B, an minus 2, plus capital C, an minus 3, what we saw was, okay, there's going to be some polynomial. Solve the polynomial equation. Well, I'll just call it roots of polynomial, okay? Because I want to have enough space to write some stuff. So roots of a polynomial, lambda cubed minus a lambda squared minus b lambda minus c. Now you see why I chose to write a times an minus 1 plus b times an minus 2 is because it just goes in the same order. All right. If you changed the way you indexed over here, if you wrote a times an minus 3 and so on, then this won't be as nicely ordered. Okay, find the roots of the polynomial. If they're distinct, if the roots are distinct, oh, by the way, how many roots do we expect? It's a polynomial. It's a 3rd-degree polynomial. We all memorized the cubic formula, right? So that's how you do this. Actually, none of us did, and it's too much of a mouthful. That's also why generally this is not really used for like, go solve this recurrence by using the cubic formula. No, it's the theory is the important thing to know that we could get to this point. And sometimes, like if you're actually solving these things, if there's some observation that there's a root, like if you already know one of the roots of this cubic, then you can, you have a quadratic left after you factor it out. But just continuing on this, if the roots are distinct, you should get 3 roots. If the roots are distinct, lambda 1, lambda 2, and lambda 3, then the magic happens. Then we got to invert that matrix, right? Then what I found out is that if I take this ABC, 1, 0, 0, 0, 1, 0, then this thing, after I invert that matrix, is some matrix, P, times the diagonal matrix, which is just lambda 1, lambda 2, lambda 3, times the P inverse. And this is zeros. Zeros all around the lambdas. Okay. Blob math time. Wait. Braden, did you just raise your hand or was that from before?
That was from before.
That was from before. Oops, sorry. I lost track. Let me keep going. Now what happens next? Oh yeah, I need to take this to the nth power, right? So what I now know is an plus 2, an plus 1, an, this guy, is equal to power the guy. So I have this p, that's what survives here, p. If I power the lambda diagonal matrix, this is lambda 1 to the n, lambda 2 to the n, lambda 3 to the n, A trick is sometimes if you expect a lot of mass in the matrix, draw the big things first and then draw the box for the matrix instead of trying to squeeze everything in. Raise to the, oh yeah, I already raised it to the power n. And then times the P inverse times this A2, A1, A0. Now, can anyone help me walk through the blob math to figure out a nice formula for an? The teaching assistants were asking, as they were preparing for yesterday's recitation, do we need to show everyone how to take inverses of matrices? And I said no, because we're using blob math. And so in this class, we never have to invert any matrices. We're too lazy to do that. Ah, yes, Abby.
We can multiply the P inverse by the A2, A1, and A0 because those are all just constants.
Yes.
And that becomes like a 3 tall column vector.
3 tall, yeah, with 3 blobs. Got it. Now what?
And then when we multiply that by our lambda diagonal, that just becomes another 3 tall where we have blob coefficients on those lambda.
Yes. Okay. Lambda 1 to the n, blob lambda 2 to the n, blob lambda 3 to the n. Okay. And now let's finish. Now what happens?
And then the last step is you have, I think it's again like a 3 tall.
Yes.
And each is just a sum of our blob times lambdas.
Yes. Perfect. So these are all like blob times lambdas. Plus, now I've just defeated what I told you, which is draw the stuff first and then write the stuff first and then draw the box. But the problem is I didn't have enough space in the first place. Okay, so it's all of those. Okay, that thing and then like similar. I'm not going to write the word same because they're not all equal. But now we're in great shape because what we have just found out is that I have a formula for an. An is the bottom thing. So we just found out that the way you solve all these things, you take the roots of the polynomial. You hope that they're all distinct. And if they're all distinct, then you have a nice formula, for sure. If they're all distinct, you're guaranteed there's a nice formula. And then that tells you, so for any n, I know that an is equal to something, some blob. Oh, we can give it a name now, okay? So the blob is now called alpha. Alpha times lambda 1 to the n plus beta times lambda 2 to the n plus gamma times lambda 3 to the n for some constants alpha, beta, gamma independent of n. Okay, now what? Now how do you finish? So we now know that we've got this general formula for all an's. How do I finish from here? Venkatesh.
You could just plug in really convenient, like lower level n's, like A0, A1, A2, and then just solve for alpha, beta.
And I want to show you something nifty that happens. Okay, so now to solve it, just like go pick any 3 n's. Usually it's 0, 1, and 2, something simple. Okay, so I'll have like 3 equations and 3 unknowns for alpha, beta, and gamma. Does that make sense? I want to find my alpha, beta, and gamma. Put in 3 equations, 3 unknowns. I'm actually going to write the 3 equations and 3 unknowns on the next screen. Okay, so what I now know is you plug in n equals 0, 1, 2. But really any 3 will do. But the 0, 1, 2 is going to be nifty. I'll find out that A0 is equal to alpha times, it's going to be lambda 1 to the power 0. Oops. Lambda 1 to the power 0 plus beta lambda 2 to the 0 plus gamma lambda 3 to the 0. I have A1 is equal to alpha times lambda 1 to the 1 plus beta times lambda 2 to the 1 plus gamma times lambda 3 to the 1. And I have A3 is equal to alpha times lambda 1 squared. Wait, what did I do? It's A2 equals. A2 equals this plus beta times lambda 2 squared plus gamma times lambda 3 squared. Remember what are your equations and what are your unknowns, okay? Remember that these lambdas are, we know them now. You presumably, we used the cubic equation, we got the lambdas. They're actually like legit numbers. The question marks that we don't know is we're solving for the alphas, betas, and gammas. These are the things we don't know. Everything else written is like known. It's like we got those like 1 plus root 5 over 2s. We got like whatever the A1, A2, A0 are. Those are legit numbers. It's like the blue stuff. Blues are the unknowns. Hey, fun question. How do you know that this is actually even solvable? Isn't it kind of scary? If I've got 3 equations and 3 unknowns, I don't always know there's a solution. Sometimes there's no solution. It's possible. Except there's a good reason actually over here why this always has a solution. And it's one reason why I showed you something else earlier today. Advait.
It looks a lot like that Vandermonde matrix again.
Oh my gosh. Vandermonde's back. Yes, the Vandermonde matrix appears twice today. It's like it appeared in the previous thing of like, hey, how do I know that I can actually invert those those V1, V2, V3s? How do I know I can invert those? Actually, it's back. I could write this whole thing as some matrix equation, right? Because I'm solving for the unknowns. The unknowns are alpha, beta, gamma. So this is actually equivalent to, that's why matrices are fun. If I got this thing, I can rewrite it as equivalent to, well, we always like to write our matrices as like a big 3 by 3 times the unknowns, and the unknowns are alpha, beta, and gamma, equals the right-hand side. Can someone tell me exactly what to write here? It might be, is it the Vandermonde? It might be a transpose or something, or who knows? We'll find out. What do we got? Help me put this thing in and tell me what that is. Zhijia.
Sure. All right. We have alpha. Wait, hold up. No. That's the wrong way. Okay, yeah. Yeah, we have alpha, and then we have.
Do you want to write an alpha here? Is that it or no? Well, what do you want to write there? That's the question.
Oh, you already have the alpha there. Never mind.
Yeah. I already have the alpha there. No problem. No problem. Let's do it.
Okay.
No problem.
Yeah, isn't it just the transpose?
Yes, it is. It is just the transpose. No, don't worry. Like this is hard stuff. Okay, we just did a whole lot of crazy stuff today. This is the lambda 1 to the 0, which is actually 1. And then this is going to be lambda 2 to the 0, which is also 1. And this is lambda 3 to the 0, which is also 1. Because that's your top row, right? You take these 3 guys, multiply by those 3 guys, and that's supposed to be A0, whatever that is. Then the second row is going to be with the coefficients lambda 1 to the 1. So this is lambda 1 to the 1, lambda 2 to the 1, lambda 3 to the 1. And then the next one is lambda 1 to the squared, lambda 2 squared, lambda 3 squared. And those equal A0, A1, A2. And actually, one thing from matrices is that if you have a matrix, it's invertible exactly when its transpose is also invertible. These things are all related. That's something related to the rank of a matrix. But we won't go deeper into that today. But it's just like the reason why this is invertible is the same thing. It's that Vandermonde again. And actually, I don't even know. Some people put the Vandermonde this way. Some people put it transposed. There are different conventions. But so whatever it is, this is like also Vandermonde, maybe. Vandermonde or transpose. Depends on where you are, and for all you know, like Vandermonde was French, so if we were here looking at his matrix, it would look like the transpose anyway because we're on the other part of the Earth. So I don't know which is the right convention. Okay, so now we know this exists. We know this exists. It's like it has a solution. It has a solution. So invertible. And that's the general solution for how you solve all these 3-term linear recurrences if there are 3 distinct roots for this polynomial. The polynomial has a name. It's called the characteristic polynomial. And this was this lambda cubed minus a lambda squared minus b lambda minus c equals 0. Actually, polynomials aren't equal 0. It's just that's the polynomial, characteristic polynomial. And if there are 3 distinct roots, bam, you're done. That's the whole thing. Okay. There's actually a reason why it's called a characteristic polynomial also. If you take a matrix class, all that we've just done is we've done a huge lesson on eigenvalues, eigenvectors, and the determinant thing. That's actually also what's called the characteristic polynomial. So that name comes twice. But we don't need to worry about the eigen stuff. We got 5 more minutes. I want to say, what happens with a 4x4? Well, at this point, all of the work that we've done, we now did it generally enough that the whole thing boils down to determining or determinating one particular matrix. So let's do the 4x4. And at this point, we don't need to do all that extra theory. Ooh, question. Remind me what we were trying to find in the first place. Yes, what we were trying to do is to find any an, okay? It's like, look, I've got this like general recursion. Here, this thing. Suppose somebody gave you an equals 50 times an minus 1 minus pi times an minus 2 plus the square root of 3 times an minus 3. How do you solve that? Well, you just write this polynomial down with the 50, the pi, and the square root of 3. Actually, I'm pretty sure those are 3 distinct roots that will come out because the probability that you get 3 distinct roots is basically 1, actually, if you choose random numbers. And then you'll get 3 distinct roots, 3 different lambdas. Once you get 3 different lambdas, you just simply solve this system of equations for the alpha, beta, and gamma, and boom, that's a general form of your equation, of your recurrence. An equals, like the first thing times whatever the first root was to the power n plus, and so on. Yeah? So let's now finish with the last piece. The last piece is going to be what to do with 4x4. Well, 4x4 is going to be an is equal to capital A, little an minus 1, plus capital B, an minus 2, plus capital C, an minus 3, plus capital D, an minus 4. So if I want to solve that, ooh, Advait, what did you want to say?
I was going to say, could you pull exactly the same thing just with 4
Yes.
instead of 3?
4 instead of 3, okay? So let's see what we can do here. So I'm just doing 4 things. And if you can see, we're just skipping steps now because we've done this like a lot of times. The key thing is, what is the matrix? I need to take some big power, nth power, of some matrix times these A3, A2, A1, A0. Can anyone give me the coefficients in this matrix? It's going to be 4x4. How does it read off? Let's take another person, Charlie.
So the top row will be A, B, C, D.
Yep.
And then the next row will be 1 and then zeros.
Good.
And then 0, 1, 0, 0.
Good.
0, 0, 1, 0.
Yes, there's a pattern. So there should be a pattern. Math is like that. So it's going to look nice. And now you got this pattern, and you're like, okay, well, we got that thing again. All we have to do is to determinate that thing minus lambdas on the diagonal. And that's it. Right? I'm not going to show all of those other steps anymore because that was the heart of the problem. And that was why I did the previous thing with enough generality, showing how you do it for 3, that whatever I did before, if it was bigger, it would be fine. So now the game becomes, how do I get, let's write 0 on the left. How do I solve 0 equals determinant of minusing lambda across the diagonal? A minus lambda, B, C, D, 1, negative lambda, 0, 0, 0, 1, negative lambda, 0, 0, 0, 1, negative lambda. Take determinant. Cofactor time. What's a good way to expand this by cofactor? We use cofactors twice. You could, but just because we're short on time, I'm going to be like, I liked what you did last time. I want to do that same cofactor again. Right column. Now if I do right column, any column is okay, but this column is going to be nice because I'm going to use induction. Okay, if I go and do this one, the reason I'm happy is because when you cofactor it, the D thing is weird, but what happens here? You get something beautiful. When you do the lambda minus lambda times the determinant of the rest, you recognize that? That's my 3x3 problem. Whenever I go from a smaller case to a bigger case, my goal is to go and find out that part of my compute is that I get to reuse what I did before. And one part of this expansion will be this guy multiplied by determinant of that thing, which we did. Okay, so let's just do it. By the way, the sign pattern here what is the sign pattern? Those are with negative signs. Is that okay with people? Because when you chessboard the guy, this is like plus, minus, so they'll have a minus sign on that. So if I do it, I get that, oops, wrong pen. I will get that 0 equals, so doing that determinant, I get d times the determinant of, well, if I lose the top row and the right column, that's going to be 1, negative lambda, 0, 0, 1, negative lambda, 0, 0, 1. And then the last one is with a negative sign also, because, no, it's not. I can't keep track. It's minus for the d, and then plus, and then minus, and then it's plus. Okay, so it's minus lambda times the determinant of what we saw before. And what we saw before is, I forgot. What we saw before had a negative lambda in it, I think. Like what we had before, yeah, I remember now. What we had before was negative lambda cubed plus plus a lambda squared plus b lambda plus c. And what I did here is I'm remembering that in the previous one, the sign was actually flipped. I did this multiplying by -1 for the previous one. Why is this amazing? Well, I still have a 3 by 3 determinant. That looks like no fun. Does anyone know how to determinate that thing? Oh, so fast. Charlie, what do you see?
If we cofactor expand on the first column, it's convenient because we just have 1.
Oh, how nice. 1 times determinant of that stuff.
And we know how to take a 2 by 2 determinant, so the whole thing is in fact 1.
Aha. And what you just found is if I ever have what's called an upper triangular matrix, the determinant is just the product of the diagonal. Because I can think of it as cofactoring along the first column at a time as I keep going. Okay? So it's a nice fact. If I ever have an upper triangular matrix, the product of the diagonal is just the determinant. That's also why there's this method of taking determinants, which is based on this Gaussian elimination. How do I erase this thing? Good. Okay. So actually, this determinant is just 1. This is just 1. There should be a negative. Oh no, there's a mistake? Yes, there is a mistake. It should have a negative. Thank you so much. Oops. Okay, there should be a negative here. Here it is. No, go back. Okay, so let's put the minus sign here. Okay, there's a minus sign. Thank you. Thank you. That's important. And we'll finish because we're about to put this all together and it's going to be amazing. Because if I put it all together up here, I get 0 equals negative d, and the rest of the stuff is plus lambda cubed, no, lambda fourth now, plus, no, it becomes minus a lambda cubed minus b lambda squared minus c lambda. Hooray! That's exactly what we expected. It's going to be another one of these beautiful things which rearranges into lambda to the fourth minus a lambda cubed minus b lambda squared minus c lambda minus d. And that's the characteristic polynomial for 4. And if you see how we did this, this should make you feel like if you really cared, you could use induction to prove this for anything. Because the way it worked is we just always you reused the previous one. That's like how an induction step works. And then there was this one piece which is always going to be whatever is there times the determinant of this thing, which is always going to be upper triangular. It's all 0 down here and just like 1's on the diagonal. So that determinant is always going to be 1. So if you actually wanted to prove that this is always going to be what you get, you could do that by induction. But for the purpose of this class, I'm happy enough just being like, you see that there's a pattern. The pattern is going to continue. And it worked for 1, 2, 3, 4. And clearly, if I wanted to, I could probably go and continue doing this out. And this is how you would then solve any 4-term linear recurrence. Get that, use the Quartic Formula. Thankfully, there is one. And then you can go and solve this system of 4 equations and 4 unknowns in alpha, beta, gamma, and delta using the first 4 terms of the A's. And you could actually get a formula. And this works for all of them, like 5, 6, 7. The only problem is you don't have a quintic formula, but that's a different topic in abstract algebra. In any case, we have now talked about the entire solution for these homogeneous linear recurrences if it just so happens that the roots of the characteristic polynomial are distinct. And that finishes everything we're going to do with the linear algebra part. Starting next time, we'll go into another way that you can think about solving these recurrences. Okay, done. Question. The idea of using the Quartic Formula, okay, oh no, yes, and then don't worry, we'll never need to know any Quartic Formula or cubic formula. It's just neat that these can be solved.